Can you people see my screen?
Yes, yeah.
The screen is visible. Perfect.
Okay. So I'm going to discuss about Metallohelicates, their chirality concepts, their luminescence, and their functional application. So let us start. So first, we should know that what is a helicate. So helicate is basically a discrete supramolecular complex constituted by one or more covalent organic strands which are wrapped around and coordinated to a series of ions defining the helical axis. So here you can see some pictures of helicates. Means in plants you can see this type of helical formation. These all are man-made architectures which basically are inspired from the helices. And this is the most renowned helix. Means this is DNA we all know, and DNA is a double-stranded helicates that also we all know. So in this lecture, I will basically focus on the metallohelicates, means those helicates which contain metals. So the term helicase was first introduced by Lin and co-workers in 1987, and there are four concepts which are basically needed to understand the helicates. So those are first molecular recognition, second is self-organization of the helicates, third one is self-assembly of the strands of the helicates, and fourth one is supramolecular programming. So now, to know about helicates, we should know about its classification. So on the basis of the number of the strands present in those helicates, we can classify helicates on as single, double, and triple stranded helicates. Means if the strands are of number 1 or 2 or 3, then respectively they are called single, double, and triple stranded helicates. Then comes homostranded and heterostranded helicates. So if the coordinated strands are identical to each other, then those are called homostranded helicates, and if the strands are not identical to each other, then those are called heterostranded helicates. So then comes homotopic helicates. So what is homotopic helicates? If um, a strand possesses a similar type of binding units, then those are called homotopic helicates. And there comes the heterotropic helicates. If one single strand possesses two different type of binding units for a metal atom, then those are called heterotropic helicates. So heterotropic helicates can further classified into, here you can see, head to head and head to tail types. Means if one metal atom is bound to one similar type of binding units from two different strands, then those are called head to head. And if they are bound to different types of strands, then those are called head to tail type of helicates. And further, it can classify it into saturated and unsaturated. Means we all know that those metal ions will bind to that helicates on the basis of their coordination number. So if the coordination number of the metal is satisfied by the strands themselves, then those helicates are called saturated helicates. And if the coordination number are not satisfied by the strands, then one extra atom or ion is needed. So those type of helicates are called the unsaturated helicates. Okay. So next, here is some example of homotopic helicates. Here you can see that this ligand can bind to first copper ion, then it can form a double-stranded helicates, and this ligand also can bind to cobalt ion and from these three-stranded homotopic helicates. And then there are two different type of strands, means heterostrands. They can bind to three copper metal ion and form a helical structure. Okay. So next, there is heterotropic helicates. So heterotropic helicates means binding units are different. So here you can see this is an example of heterotropic helicates. Means this ligand can bind to one palladium metal to palladium metals and from these heterostranded helicates. So these are basically head to tail type of helicates, and this is head to head type of helicates. Formed by two different metals, and these are one unsaturated type of heterotropic helicates. Means this unsaturation is satisfied by this OSC type of ion. So now the further classification is single-stranded linear helicates. This is an example of single-stranded. Here you can see this one single strand can bind to two palladium metal ions and from a helicate. And then comes triple-stranded helicates. Means three these type of ligands can bind to three metal atom and from a helicate. Then comes this quadruple-stranded helicates. Means four these ligands are bound to these two metal ions and from quadruple stranded helicates. And then comes trinuclear circular helicates. In previous, all the helicates are linear, but these from the circular type of structure. Here you can see that these ligands can form this circular type of structure with these three copper ions. So next we'll discuss the chirality of the Metallohelicates. So we all know that what is a chiral molecule? So chiral molecule is an object or a system which is distinguishable from its mirror image and that cannot be superimposed onto it. So best example of chirality is basically human hands, and then comes achiral molecules which are opposite of it, um, means a object or a system is not distinguishable from its mirror image. So, there a complex molecular system has three different types of chirality. The first one is chirality due to enantiomeric ligand, means R or S type of chirality. Then comes chirality at the metal center, delta lambda type of chirality. And then comes chirality due to orientation, means P or M type of chirality. So, this is an example of delta lambda type of chirality. Here you can see one metal center, and if the ligands are oriented in clockwise fashion, then those are called that delta type of chirality. And if surrounding the metal atom, if the ligands are rotated in anti-clockwise fashion, then those are called the lambda type of chiral molecule. So then comes this P helicity and M helicity. Those are basically similar to that previous one. Means if the helicity is in clockwise fashion, then those are called M helicity. P helicity. And if those are in anti-clockwise fashion, then those are called M helicity. So in case of helicates, we can see this type of chirality. Means first, you can see it if the two strands are both of delta type of chirality, then those are called the delta delta type of helicates. And if that two ligands are both anti-clockwise, means both are lambda type of, then those are called that M type of chirality. And then if one strand is of lambda type and one strand is of delta type, then this type of helicates are called mesohelicates. Okay, that delta lambda type of chirality is present. So, what is the functional applications of this chirality? So, here I will discuss one functional application, which is enantiomeric resolution of asymmetric binuclear double-stranded cobalt 3. So, here you can see I took one ligand. This is a ligand, and this has a spacer between them. So, which is a spacer means uh, with these to nitrogen and oxygen, these can donate their electron to bound to a metal atom, and similarly these three also can donate electron to bind to a metal atom, and the space between them is called the spacer. So here present CH2 type of spacer, and if there is one CH2, then this will be H2 type of ligand, and if the n equal to 2 means 2 CH2 is present, then it is H2 type of spacer, and means H2 type of ligand. And if there are three spacers, means three CH2 type CH2, then that ligand will be H2 3 type. Okay, so with reacting with this COCl2, it can form means three different types of helicates, and these are both delta delta type, lambda lambda type, and delta lambda type. So the question is first how we can separate those enantiomers. Means in a reaction all are present, means they are basically kind of racemic mixture type. Both delta delta and lambda lambda type are present. So how we can separate them? So we can separate them by the method of column chromatography. So how? So we all know that column chromatography method needs a mobile phase and a stationary phase, and those both phases are chosen in such a way that their interaction with one enantiomer will be stronger than the other. So this is necessity for separating them. So here I choose cellulose as a stationary phase, and mobile phase will be the slurry mixture of NaCl, cellulose, and obviously the helicate. So what is the method? So first in a burette, if I take that stationary and mobile phase and drop by drop, if I add that acetonitrile, then first one light brown color of solution will come out. Okay, so these are that mesohelicates, and then one green colored solution will come out. This is of lambda lambda type, and then one means pink or reddish type of solution will come out. This is delta delta type. Okay, so the question then will be arise that how will know that it is delta delta type, or this is mesocate, or this is lambda lambda type. Okay, so for this we have to measure that CT spectra. So that CT spectra can confirm the presence of enantiomer. So how this can confirm the presence of enantiomer? So that CT spectra will not be present in case of achidal mesocates. Hello?
Yes, yes.
Yeah, you can continue.
Okay. Okay. So that CT spectra is absent for the achidal mesocates. But they are present in case of that enantiomers, means that second and the third extract which we found from that column chromatography method. In that case we can found them. So how we can found them? There will be a positive and a negative photon effect. So if I take this particular graph, here you can see that this green is denoted by that M helicate, and red will denote that P helicate. So when that green is lower, that M is higher, and when and vice versa. So these are called the positive and negative pattern effect. And if if in a CT spectra we can find this type of pattern, then we can confirm that one enantiomers is present in that solution. Okay. So first, so how we use that enantiomers in our means practical applications? So they can be used as catalyst. So that result enantiomer are used as catalyst for asymmetric organic transformation, and expected products of excellent yields can be produced. So my reaction here, I take one nitroaldol reaction where that cobalt 3 helicates can act as a catalyst. Okay, so this reaction is occur, and if I don't use catalyst, means catalyst is blank, then you can see the yield is only 56%. But when I start using catalyst, means this delta delta and lambda lambda type of catalyst, then you can see that yield is too high, means this is 92% yield and this is 90% yield. And in case of that all three type of helicates, high yield is found. And in case of racemic mixture, the yield is also high, like this 90% yield. Here you can see 92% yield. Here you can see also 92% yield. Okay, but the enantiomeric excess is only present in case of these two means chiral type of helicates, means delta delta and lambda lambda. In case of racemic mixture, there will be no enantiomeric excess. So by using these helicates, we can find that specific yield of a reaction, which if I not use those catalysts, then we cannot detect that yield in our needed way. So if things there, one thing can be seen, that if I repeat the experiment for too many times, like 10 or 12 times, then ultimately that enantiomeric excess will be zero. Okay, so how? Means if I use that, means this delta type of helicate, then the racemization of enantiomerically pure helicates to mesocates is obtained. Means this delta delta can from delta lambda type, or also that lambda lambda can from delta lambda type. So this is called that racemization can occur and yield can be zero. So this is another type of reaction. So this is called benzylation reaction. And in this case, we also use that helicate as a catalyst, and we can find that excellent yield of that reaction. And without catalyst, we can't have that much yield. Okay. The similar way that catalysis reaction is also occurring. Then comes another property of these helicates, and this one is the most interesting property of those helicates. So here I will discuss the luminescent property of lanthanide helicates. Okay, so first one thing can be asked, that why I use specifically lanthanides. So we use lanthanides. Basically, there are four properties shown by the lanthanides. First one is large stroke shift. Means lanthanide show very broad stroke shift, and by that property we can detect lanthanide in a very specific way in any solution. And then narrow emission band, and then comes that long excited state lifetime, and then come high quantum yields. And another very interesting property shown by that lanthanide is, this is so antenna effect. Okay, so what is antenna effect? Means if we directly excite that lanthanide ions, then emission band can be formed, but they are not very specific. But if we use one antenna, means another type of the helicates around it, means here helicates can be used as antenna, and these have very high molar absorption coefficient, and lanthanide has very low molar absorption coefficient. So if we excite that antenna type of molecule, means here that helicate, so that energy can be transferred through, means that energy can be transferred to the lanthanide ions. So here you can see the energy transfer, and one emission band can be detected, and this emission band is of specific very specific wavelength. It will be of very specific frequency, so we can detect it in a very easier way. So here you can see the solutions of that lanthanide ions, and it can show different types of luminescence and different colored luminescence. So then applications of that sensing. So how we can use that sensing? So application of the luminescence property of the lanthanide. The first one is sensing. We can sense a specific type of helicate. Means if we know that the lanthanide can bind with that helicate, so in a solution we can easily found that helicates with the help of the luminescence shown by the lanthanide ions. And then cell imagining, then responsive probes and lamps and displays and lasers and telecoms, all these have this lanthanide luminescence. And if we focus on this application of sensing and cell imagining, we can see that it can sense the small molecules. Okay, in small molecules such as anions, these all type of anions can be sensed, and these cations. And in previous researches, it is very well reported. And then, if in case of biological anions like ATP, ADP, AMP, or phosphate, these also are very well reported in literature. But selective sensing of the nucleoside phosphate species means how we can selectively sense only AMP, ADP, or ATP. This is a ongoing research process, and people are trying to find it in a very well manner. So why this is very important to detect that AMP. So what is the importance of phosphate? We all know that these excess phosphates in CKD causes severe cardiovascular and kidney problems, and also if ATP deficiency causes Parkinson disease and hyperglycemia. And it is also very important. It has very important role in DNA synthesis, cell imagining, or transport across the membrane. So any biological system, it is very important to detect the presence and the quantity or the pathway of the phosphate ions or AMP. So how AMP can bind with a metal ion? So these AMP basically can act as ligands. Okay. So AMP, ATP, ADP, ADP, and AMP, this basically differs due to the number of phosphates. I mean, it is triphosphate, three phosphates are there. It is diphosphate, two phosphates are there. And this is monophosphate, means only one phosphate is there. Okay. And this is another type of binding site. So with metal ion, that two binding sites can be bound with that metal ion and from this helical structure. And spacer is also there. Here in this case, this structure is acts as a spacer. So 2 AMP with 2 metal ion here lanthanide can form a helicate structure. So this is the skin how this will bind.
So I have a one question. Uh,
Yes.
yeah, go to the last slide. Yeah, so there are the two phosphate site, na. So how I detect that which one will be bind? Like you give the two spacer there, one for this middle one, another for this another phosphate site. So how do you confirm this thing?
Oh, sorry. Okay, so basically, this phosphate is more likely to bind with any kind of metal ion. Means these are extreme. Means the last phosphate will be more efficient to bind with that metal ion. Means there will be that OH which can be easily bind with the metal ion and satisfy that coordination number of the metal ions. And here you can see that these all O are means binded and form already formed a bond, but these are free.
Okay.
Okay, also, I just had one quick additional question.
Yes.
Like, say the metal ions are binding like that. Will it be
Uh-huh.
something like after they bind? Will it be something like say 90% of them have bounded in the P up there, and then 10% of them have not bounded there and somewhere maybe in the other side they have bound. Can it be like that?
Uh, Means see, if I took one ADP,
Hmm.
okay, so one ADP it can bind with this phosphate, but if there will be means a solution, then there are means metal ions. So the means in the formation can be more ADP and more AMP are free in the solution, and lanthanide can bind with some of them, but binding with be in that fashion only. Means
Okay.
it cannot be left free like that.
Okay, so it will bind only with that.
Yes.
It's not about probability. Okay.
No.
Okay, thank you.
Acha, also one question I did not ask this at that time. So, what are the specific property of these helicates which makes it efficient for catalysis? Like you saw, na, that for the catalysis it is work very good. So,
Oh, yes.
yeah. So, what are actually the specific property of the helicates? That means that helicates are like, and you say that is useful for catalysis. So, how it's making the catalysis thing? Because like we all know the transition metals are good catalysts, but what is the role of helicates here actually?
See, transition metals are very good catalysts, and these similar means that similar property is used in this in that case of helicates also. But in case of transition metal, we cannot have this kind of means enantiomers. You can see that means it is one CD signal intensity. Okay, means if they are means if there will be the presence of this enantiomers means delta delta lambda lambda type of different chiral catalyst means there will be if there will be chirality then reaction will be more profound. You can see that two different type of means product will be there means one is 2s or 1 or 2 r. So how it can be find means if there are not in the presence of that means if there are no chirality then how this kind of products will be there it's only yeah if we use that metal ion okay only if we use that metal ion then this will be not be there means that catalysis means that what I can say that enantiomeric property will not be there in case of helicates in
So
case
that
of
means
not
you are
helicates
saying that if there are like two type of products. So actually, these type of helicates are producing one specific product as a major amount. That means one specific
yes yes
enantiomer.
here you
Okay,
can
so
see that
in other
major
case
means
it
it is
will be an
in
enantiomer in general
means
case. And in blank case,
yes
in
if
blank.
the yes in blank case there will be no means there will be no major or minor product means in blank case like this no catalyst will be there then only one kind of reaction then you cannot see that how that reaction is happening and this
Okay, I
is
get.
okay so I was here I think so the formation of targeted lanthanide helicates so here I use this specific type of helicate and this can bind with two lanthanum ions and from these two type of helicates okay so, so in a means in screening effect in aqueous buffer there are the presence of different type of anions but in different type of anions we can see that there is very low means there is very low emission intensity but in case of AMP this specific type of helicate can show a very high emission intensity so thus we can basically detect the presence of AMP in a system and not AMP we all know that ATP can from like means ATP can from first ADP and one phosphate, then it can further divide it into AMP plus two phosphate. So these all things we can denote by this type of method. So how that only AMP can means only AMP can show that specific means reaction. So this is our structure of the helicate. So if AMP is reacted with that, then one one europium ion, there will be seeing the displacement of H2O in the case of one europium ion and ADP is added with this, or you can see that this phosphate is adding with this europium. So here, if I detect that ATP in a reaction, then the last phosphate will be bind with this. Means you can get your answer, I think.
Yeah, that means we can design the specific helicates for ATP and AMP like that,
Yes,
na?
yes, we can design it. And this is only a mechanism from a paper. You know, there are different papers with different type of helicates. And then that, oh sorry, huh? And then that then the next reaction will be this will bind to another europium. Okay, and one this banana type of structure will be there. And for this specific binding with only AMP, these helicates can show a specific quantum yield in case of only AMP. Means there will be charge interaction between them. So we can detect the presence of AMP in any system by using a specific helicates. So this is all. Thank you.